In the early 1880s, chemists Rainer Ludwig Claisen and J.G. Schmidt independently published a method for systematically coupling carbon skeletons together. The mechanism relies on a precise electronic mismatch. A nucleophilic enol or enolate attacks the electrophilic carbonyl carbon of an acceptor molecule. This initial addition yields a specific intermediate, a beta-hydroxycarbonyl compound, universally known as an aldol. But relying on this initial step induces a physical organic problem. The formation of the new carbon-carbon bond operates as a precarious, highly reversible equilibrium. When reacting bulkier molecules like ketones, steric hindrance actively drives the reaction in reverse, favoring the starting materials over the products. To utilize this reaction for complex molecular architecture, chemists must find ways to actively break, manipulate, or bypass that reversible equilibrium. Without aggressive thermodynamic or kinetic interventions, the carbon-carbon bond remains unstable, resulting in a chemical flux that prevents the formation of a single, high-yield target. The limits of this reaction become obvious in a crossed aldol sequence, where two distinct, enolizable carbonyl compounds are mixed. This matrix shows the statistical outcome. Because both molecules possess acidic alpha hydrogens and electrophilic carbonyl carbons, the reaction generates 4 distinct isomers. Half of this output represents a total loss of atom economy, as the molecules undergo unwanted self-condensation, rather than reacting with each other. The classical workaround relies on restricting nucleophilic initiation. Chemists introduce an acceptor molecule that strictly lacks alpha hydrogens, like benzaldehyde or formaldehyde. Exposing these specific, non-enolizable aldehydes to basic conditions introduces a severe competing pathway known as the Cannizzaro reaction. The Cannizzaro pathway induces rapid disproportionation. Before the bonds form, the basic medium oxidizes aldehydes into carboxylic acids and reduces them into primary alcohols. Relying strictly on basic thermodynamic equilibria guarantees statistical impurity and actively invites parasitic side reactions that destroy the necessary synthetic precursors. The most direct method to force the reaction forward is to dehydrate the beta-hydroxy intermediate. Under basic conditions, this elimination proceeds through the E1CB pathway, a mechanism distinct from standard concerted E2 or carbocation-driven E1 eliminations. This reaction coordinate profile maps the E1CB pathway. The first step requires overcoming a steep energy barrier as a base deprotonates the alpha carbon, forming a discrete resonance-stabilized carbanion. The second step features the forceful expulsion of a hydroxide ion, forging the final carbon-carbon pi bond. In standard organic chemistry, a strongly basic hydroxide ion is universally recognized as a poor leaving group. Yet, as the energy curve drops, we see the thermodynamic justification. Expelling the hydroxide yields a highly stable conjugated system. The extended delocalization of pi electrons across the new double bond and the carbonyl group creates a thermodynamic sink. The entire condensation sequence becomes strictly irreversible. If an alpha-beta unsaturated enone is not the desired target, chemists must abandon thermodynamics entirely and rely on strict kinetic control. This requires a spatially demanding non-nucleophilic base like lithium diisopropyl or LDA. The base quantitatively abstracts a proton from the least hindered alpha position. By running this reaction at cryogenic temperatures of -78 degrees Celsius, the kinetic enolate is locked into place, preventing any proton equilibration. In 1973, researchers at the Tokyo Institute of Technology developed a methodology to bypass the sensitivity of those lithium enolates. The Mukayama-Aldol reaction utilizes highly stable, easily isolatable trimethylsilyl enol ethers as enolate equivalents. To facilitate the reaction, a Lewis acid, specifically titanium tetrachloride, coordinates with the acceptor aldehyde, increasing its electrophilicity. This 3D diagram models the geometry of the reaction. On the left, standard metal enolates require a highly ordered, closed-cyclic Zimmermann-Traxler transition state. On the right, the Mukayama reaction proceeds through an open, flexible transition state. This precise open trajectory permits a controlled cross-aldol reaction between two different ketones, physically eliminating the risk of self-condensation. By combining stable Silyl traps with Lewis acid mediation and open transition states, synthetic chemists can dictate the exact trajectory of cross-condensations. The reversibility of the initial aldol addition, cleaving the beta-hydroxycarbonyl back into its constituent parts, is known as the retro-aldol fragmentation. In the total synthesis of dense, highly oxygenated natural products, chemists engineer this fragmentation directly into their pathways. The synthesis of the polycyclic macrolide xeragosic acid C utilizes an intramolecular aldol cyclization to construct its core backbone. Forcing these atoms into such a tightly packed architecture generates severe molecular ring strain. To relieve this strain, the synthesis employs a regulated retro-aldol-re-aldol sequence. The atoms repeatedly connect, break apart, and reconnect in slightly different geometric arrangements. The moment the system locates its global thermodynamic minimum, a rapid acetylation step permanently traps the desired intermediate. In these strained environments, thermodynamic reversibility functions as an error correction algorithm, preventing the system from freezing into non-viable steric configurations. The ultimate physical challenge in aldol chemistry involves the intramolecular macrocyclization of long-chain dialdehydes to form large 11 to 17-membered rings. This probability map visualizes the entropy problem blocking the reaction. The statistical likelihood of one flexible chain colliding with another is significantly higher than its two ends finding each other. This entropy imbalance ensures chaotic polycondensation dominates the reaction flask. Biological systems navigate this exact issue. Class 1 and 2 aldolase enzymes utilize restricted active site pockets to physically isolate reacting substrates from the bulk solvent. Synthetic chemists replicate this architecture using supramolecular cavitans, rigid, bowl-shaped receptor molecules containing hydrophobic internal cavities. The dialdehydes and the cavitans are placed together into a purely aqueous environment. Hydrophobic forces push the nonpolar alkyl chains of the dialdehydes out of the water and into the interior of the cavitan. This absolute molecular confinement forces the substrate into a pre-organized U-shape, pushing the reactive terminal ends into immediate proximity and suppressing all intermolecular alternatives. By navigating the thermodynamic and kinetic constraints of the aldol bond, chemistry has moved beyond statistical mixtures toward the spatial precision required for macromolecular synthesis.